Laws of Motion, Lesson 4. So, as a starter, I've got 3 terms that I want us to have a think about: thinking distance, braking distance, and stopping distance. This should be familiar to you from GCSE. These terms were all part of the physics spec there. So, thinking distance, to do with our reaction time, the distance travelled during the time taken to react. The braking distance, then, thinking distance is going to be about your reaction time. You seeing a hazard when you drive along in the car or riding your bike or whatever, and thinking to yourself, I've got to react, but not actually reacting. The braking distance then is going to be during the time whilst you are reacting, like the distance travelled whilst the brakes are applied safely. So you've got time to think in your head, I need to apply the brakes now, and then to move your foot onto the pedal and apply the brakes. Note that both of those I've underlined the word distance, haven't I? So like you might think, oh, thinking distance, how long it takes to stop. Well, it's not how long it takes to stop, because how long implies a time. And we're not measuring a time, we're measuring the distance. It's thinking distance, how far you travel during the time taken to react. So remember, we've got to say about how far. That's a common mistake in exams where they won't give you the mark if you say how long, because that implies a time. Also note that the braking distance is for when the brakes are applied safely, as in without skidding. So if the car skids and you're not braking safely, it's going to take longer to stop. Stopping distance, the final one, thinking distance plus stopping distance, the total distance taken to stop the car from seeing the hazard. So made up of the thinking distance, the distance travelled during the time taken to react, and the braking distance, the distance travelled while the brakes are applied safely. So we're on about vehicle safety this lesson. It's going to be all about how we apply the knowledge of Newton's laws of motion to vehicle safety. It's the same spec reference, Newton's laws of motion, knowledge and application of the 3 laws in appropriate situations. So we'll look at how we apply them to vehicles to make vehicles safe, or how we look at that in a physics context. So we would try to distinguish between braking distance and stopping distance and how road conditions affect these. So we'll look next about factors that are going to affect braking and stopping distance. We'll think about describing the force on a moving body if it's suddenly stopped, for example in a road accident, and explain what should be done to minimise the risk of occupants in a vehicle in physics and in the design of the car. So it's really, what's braking distance, what's stopping distance, and what's thinking distance, and how can we apply physics, the physics of moving bodies, to a specific example of a vehicle, like a road accident, or what we can do to reduce risk in that sort of thing. So what factors might affect these distances? We could start off and think about the thinking distance. We said the thinking distance was the distance travelled during the time taken to react. It should be clear that there's a number of things that are going to affect it, like for instance, anything that's going to increase your reaction time is going to make a difference. If we're going to write out what thinking distance is in terms of our SUVAT, we could do that, couldn't we? Because that car's travelling along at constant speed. It's not started decelerating yet. So really, all we've got for a distance is speed times time. Speed is going to be the initial speed, u, times by the thinking time. So we'll say that that is thinking distance is u t naught, where t naught is the time taken to react, the reaction time. So that reaction time then, what's going to increase that? Tiredness, definitely. If you are tired, you react slower. There's some studies saying that being really tired can have a similar effect to being under the influence of alcohol, for instance. At a greater speed, it will take longer to stop, necessarily because thinking distance is u t naught. So if u, the initial speed, is faster, it's going to take a longer distance to stop. Most of the other ones will be about t0, the reaction time. Like, for instance, distractions. Anything in the car that distracts you and stops you from reacting as fast as what you would is going to make a difference. So if you've got a mobile phone that you're checking or talking into, if you've got passengers in the car that you're having a conversation with, if you've got loud music playing, things like that. And finally, the influence of alcohol or other drugs is going to have an effect on your reaction time. It's going to slow it down. What about the stopping distance then? We said that the braking distance, the time it takes to brake the car safely once the brakes are applied without skidding. Well, if we're trying to think about that in terms of our SUVAT equations, then the braking distance is going to be u squared divided by 2a. I've just realised that's not formatted right. U squared divided by 2a from the no t equation, which is v squared equals u squared plus 2as. Because we're slowing down to 0, that v squared term goes to 0, so we've got 0 equals u squared plus 2as. It's s that we want, the distance. So if we put u squared on one side and minus 2as on the other, to get s on its own, we divide by 2a. U squared divided by 2a, assuming the deceleration is constant, which, constant braking force applied with the pedal would be reasonable. Next, same as in the previous example, a greater speed is going to increase the braking distance. From this term here, u squared divided by 2a, the braking distance depends on the initial speed and how fast you slow down the deceleration. So anything that will increase the braking distance, it's increasing the initial speed, so going faster, or decreasing the deceleration, anything that causes you to slow down slower. So greater speed is the u term. What is going to affect the a term, the acceleration? Well, poor road conditions. The road could be icy or wet, so you wouldn't slow down as quickly, or the road could be in poor repair, or it could be a poor road surface, so there might be gravel or mud, for instance. Both of those would mean you've not got as much friction with the road, so the braking force isn't as large. In addition to the road itself, there could be the car. So the poor car condition is to do with friction, isn't it? So we're thinking bald tyres. If your tyres are worn, then your car's not going to stop as well. Worn brakes, that should go without saying, shouldn't it? If you've got worn brake pads, you're not going to be able to stop as well. And also a heavy load. Thinking Newton's second law, F equals ma, that a, the acceleration that we want to slow down, is caused by the braking force and is impacted by the mass. So if your car has got a bigger mass, it's going to take more force to slow it down. So if your car is overloaded, that will make a difference as well. So what if we tried to write stopping distance? It is thinking distance plus braking distance. So we wrote it down, u t0 plus u squared divided by 2a. We should be able to think about deriving them from the SUVAT equations ourselves, which, as I said on the previous slide, that's reasonably straightforward, isn't it? Thinking distance is constant is zero acceleration, so we can just use speed equals distance equals speed times time. With the previous slide, the braking distance, we used a no-t equation, v squared equals u squared plus 2as. And that's it about stopping distance and braking distance and thinking distance. We're trying to apply what we knew about Newton's laws then. So it's another thing to think about then is impacts of collisions. What force will the driver or the passengers of the car experience? We could measure the impact of a collision in terms of the deceleration it causes. So the impact force is equal to mass times acceleration. The deceleration on that mass tells us what the impact force is. we could easily represent that using multiples of the acceleration due to gravity, only because that's something that we're familiar with. Like how much gravity pulls us down. If it were pulling us down twice as much, we could say it was 2g. If it was pulling us down 5 times as much, 5g, etc. That probably looks familiar to you, doesn't it? Like off of roller coasters and aeroplanes. Or it was 7g, for instance, implying how much force it is compared to the force of gravity. So if we're looking at an example, if the acceleration is minus 30 meters per second squared, that's about minus 3g, as in it's 3 times about 10, 9.81. So the impact force given by Newton's second law, F equals ma, becomes F equals minus 3 mg, 3 times the magnitude of the object's weight. And that's what we're saying when it's 3 g's of force, we mean it's 3 times the magnitude of the object's weight. So, what do we need to be able to do? In our plenary, why do the following devices help keep the passengers in a car safe? Seatbelts, airbags, crumple zones, and ABS. All of these are focusing on Newton's second law. So, I've put on the screen, force equals rate of change of momentum. Change in momentum divided by change in time, dp dt. So, we need to think about, in terms of those 4 things, what is going on with that. Seatbelts. How do seatbelts work? Do seatbelts stop you immediately? No. Seatbelts have a bit of give before you are jerked stopped. Think of all of those times you've struggled to put the seatbelt on because it keeps catching. It's that catch. It lets it go a bit and then stops you. So what it's doing is it's increasing the time of the collision. If you increase time in this equation, change in time is larger. Well, that will mean that the force is less. If you've made the denominator bigger, the fraction gets smaller. Same is going to be true for airbags. With airbags, the airbag inflates out of the steering wheel or side of the car. It provides a cushion of air to slow down your deceleration so that the time it takes is longer. An increased time leads to a lower force. Crumple zones. What are crumple zones? And bits of some cars are designed so that they crumple in an accident. What's that going to mean? It's going to mean that the change in momentum happens over a longer time. Same thing. Lower force because we've got a longer time, so the rate of change of momentum is smaller. If you were answering a question about that, you're thinking your 3 points are those. You're saying about the time for the change of momentum is longer. That means the rate of change of momentum is smaller, so the force is smaller. 3 points to that, linking them all together. What about ABS? ABS is an anti-lock braking system. If you brake heavily in most cars, then the brakes go thud, 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 and apply and unapply themselves really, really rapidly, even though you've got your foot down hard on the brake. What that is, it's a special feature designed to make the car not skid. So by applying and unapplying the brakes, it means that the car gets more friction with the road. If there is a greater frictional force, then the car sticks to the road better. It doesn't skid. Your braking distance decreases. And a smaller braking distance means that we can stop sooner. There's less chance of a collision. And that's it for this lesson.